Okay, so let's dive first. Today we'll talk about training neural networks again, and then I'll give you a bit of an intro to convolutional neural networks. Before we dive into the material, just some administrative things first. First, I didn't get a chance to actually introduce Justin last lecture. Justin is your instructor also for this class, and he was missing for the first 2 weeks. And so you can ask him anything about anything. He's very knowledgeable. Maybe that's an overstatement, but I don't know. Okay, and the assignment 2 is out as a reminder. It's quite long, so I encourage you to start earlier. And it's due basically next Friday. So get started on that as soon as possible. And you'll implement neural networks with the proper API of forward-backward passes, and you'll see the abstraction of a computational graph. And you'll implement also batch normalization dropout, and then you'll actually implement convolutional networks. So by the end of this assignment, you'll actually have a fairly good understanding of all the low-level details of how a convolutional neural network classifies images. Okay, so where we are in this class, just as a reminder again, we're training neural networks, and it turns out that training neural networks is really a 4-step process. You have an entire data set of images and labels. We sample a small batch of that data set. We forward propagate it through the network to get the loss, which is telling us how well we're currently classifying this batch of data. And then we back propagate to compute the gradient on all the weights. And this gradient is telling us how we should nudge every single weight in the network so that we're better classifying these images. And then once we have the gradient, we can use it for a parameter update where we actually do that small nudge. Last class, we looked into activation functions and an entire zoo of activation functions and some pros and cons of using any of these inside your neural network. A good question came up in Piazza. Someone asked, why would you even use an activation function? Why not just skip it? And the question was posted, and I forgot to really address this very nicely in the last lecture. But basically, if you don't use an activation function, then your entire neural network ends up being one single linear sandwich. And so your capacity is equal to that of just a linear classifier. So those activation functions are really critical to have in between, and they are the ones that give you all this wiggle that you can use to actually fit your data. We talked briefly about data preprocessing techniques, but very briefly. We also looked at the activation functions and their distributions throughout the neural network. And so the problem here, as you recall, is we have to choose this initialization for our weights. And in particular, there's the scale of how large we want those weights to be in the beginning. And we saw that if those weights are too small, then your activation in a neural network, as you have a deep network, goes all towards 0. And if you set that scale slightly too high, then all of them will explode instead. And so you end up with either supersaturated networks, or you end up with networks that just output all zeros. And so that scale is a very tricky thing to set. We looked into the Javier initialization, which gives you a reasonable kind of thing to use in that form, and that gives you basically roughly good activations or distributions of activations throughout the network in the beginning of training. And then we went into batch normalization, which is this thing that alleviates a lot of these headaches with actually setting that scale properly. And so batch normalization makes this a much more robust choice, so you don't have to precisely get that initial scale correct. And we went into all of its pros and cons, and we talked about that for a while. And then we talked about the learning process, and so I tried to show you kind of tips and tricks for how you actually babysit these neural networks, how you get them to train properly, and also how you run cross-validations and how you slowly converge over time into good hyperparameter ranges. So we talked about all of that last time. So this time we're going to go into some of the remaining items for training neural networks, in particular parameter update schemes, I think, for the most part. And then we'll talk a bit about model ensembles, dropout, and so on. Okay? So before I dive into that, any administrative things, by the way, that I'm forgetting? Not necessarily? Okay. So parameter updates. So recall that there's this 4-step process to training a neural network, and this is a pseudocode really in what it looks like. We get a data batch, evaluate the loss, evaluate the gradient, and perform a parameter update. When I talk about parameter updates, we're specifically looking at this last line in here, where we are trying to make that more complex. So right now what we're doing is called just gradient descent, where we take that gradient and that we've computed, and we just multiply it, scaled by the learning rate, onto our parameter vector. We can be much more elaborate with how we perform that update. And so I flashed this image briefly in the last few lectures, where you can see different parameter update schemes and how quickly they actually optimize this simple loss function here. And so in particular, you can see that SGD, which is what we're using right now in the 4th line here, that's SGD in red. You can see that that's actually the slowest one of all of them. So in practice, you rarely ever use just basic SGD, and there are better schemes that we can use, and we're going to go into those in this lecture. So let's look at what the problem is with SGD. Why is it so slow? So consider this particular slightly contrived example here where we have a loss function surface. So these are the level sets of our loss. And suppose that it's elongated along one direction much more than another direction. So basically, this loss function here is very shallow horizontally, but it's very steep vertically. And we want to, of course, minimize this. And right now, we're at the red spot, and we're trying to get to the minimum, denoted by the smiley face. That's where we're happy. But think about what the trajectory of this is in both x and y directions of SGD if we try to optimize this landscape. What would that look like? So what would it look like horizontally and vertically? I see someone's plot. So what are you plotting out there?
Bounce more up and down, I guess.
Okay. And why is it okay? So why is it going to bounce up and down like that? And why is it not making a lot of progress?
Because the local gradient is oriented.
Right. So the local gradient is basically has this form where when we look at the gradient horizontally, we see that the gradient is very small because this is a shallow function horizontally. But vertically, we have a large gradient because it's a very steep function. And so what's going to happen when you roll out SGD in these kinds of cases and you end up with this kind of pattern where you're going way too slow in horizontal direction, but you're going way too fast in the vertical direction. Okay, so you end up with this ugly jitter. So one way of remedying this kind of situation is what we call a momentum update. So the momentum update will change our update in the following way. So right now, we're just incrementing the gradient. We're taking the gradient, and we're integrating our current position by that gradient. In the momentum update, instead, we're going to take the gradient that we've computed, and instead of integrating the position directly, we're going to increment this variable v, which I call v for velocity. So we're going to, and we'll see why that is in a bit. So we increment this velocity variable, v, and instead, we're basically building up this exponential sum of gradients in the past, and that's what's integrating the position. This mu here is a Hoppe parameter, and mu is kind of a number between 0 and 1. And what it's doing is it's decaying the previous v and adding on this current gradient. So what's nice about the momentum update is that you can interpret it in a very physical terms. And in the following way, basically, using momentum update corresponds to interpreting this as really a ball rolling around this landscape. And the gradient in this case is your force that the particle is feeling. So this particle is feeling some force due to a gradient, but instead of directly integrating the position, this force, F equals ma in physics, so force is equivalent to acceleration there. And so acceleration is what we're computing. And so the velocity gets integrated by the acceleration here. And then the mu times v has the interpretation of friction in that case, because at every single iteration, we're slightly slowing down. And intuitively, if this mu times v was not there, then this ball would never come to a rest because it would just jigger around the loss surface forever, and there would be no loss of energy where it would settle at the end of a loss function. And so that's the momentum update. It's taking this physical interpretation of optimization where we have a ball rolling around and it's slowing down over time. And so the way this works is, what's very nice about this update is you end up building up this velocity. And in particular, in the shallow directions, it's very easy to see that if you have a shallow but consistent direction, then the momentum update will slowly build up the velocity vector in that direction. You'll end up speeding up and up across the shallow direction. But in the very steep directions, what's going to happen is you start, of course, jittering around, but then you're always being pulled up the other direction towards the center. And with the damping, you end up kind of oscillating to the middle. And so it's kind of damping these oscillations in the steep directions, and it's kind of encouraging these It's encouraging progress in these consistent shallow directions. And that's why it ends up improving the convergence in many cases. So for example, here in this visualization, we see the SGD update in red. Momentum update is in green. And so you can see what happens with the green one. It overshoots because it's built up all this velocity. So it overshoots the minimum, but then it eventually ends up converging down. And of course, it's overshot, but once it converges there, you can see that it's converging there much quicker than just a basic SGD update. So you end up building up too much velocity, but then you eventually get there quicker than if you did not have a velocity. Okay? So that's the momentum update. I'll go into a particular variation of the momentum update in a bit. I just wanted to ask, are there any questions about the momentum update at this point? Go ahead.
Do you typically use one mu for everything, or do you have a different mu for each layer? Or have something?
Yeah, thank you for asking. So do we use a single mu? And usually we do. That's a single hyperparameter. And usually it takes some values of roughly 0.5 or 0.9. And usually people sometimes, this is not super common, but people sometimes annihilate from 0.5 to 0.99 slowly over time. But it's just a single number. Go ahead.
For this SGD example that you had, Couldn't we avoid that problem with a smaller learning rate?
Yeah, so you could avoid this with a smaller learning rate, but then the issue is if you had a slower learning rate, this learning rate is applied globally to all the directions in the gradient. And so then you would basically do no progress in the horizontal direction, right? You wouldn't jitter as much, but then it would take you forever to go horizontally if you had a smaller learning rate. So it's this kind of trade-off there. Okay? So I'd like to describe a modification on the, oh, sorry.
How do we initialize the velocity, or does it matter?
Oh, thank you. So V here, the question is how do you initialize velocity? You usually initialize with 0. And it doesn't matter too much because you end up building it up in the first few steps, and then you end up with this. If you expand out this recurrence, you'll see that basically it's a exponentially decaying sum of your previous gradients. And so once you've built it up, you have a certain amount of it. So initialize at 0. Okay? So a particular variation of momentum is called something called Nesterov momentum, and or Nesterov accelerated gradient descent. And the idea here is we have the ordinary momentum equation here. And the way to think about it is that your x is incremented by really two parts. There's a part that you've built up some momentum in a particular direction. So that's the momentum step in green. That's the mu times v. That's where your momentum is currently trying to carry you. And then you have the second contribution from the gradient. So the gradient is pulling you this way towards the decrease of a loss function. And the actual step ends up being the vector sum of the two. So the blue is what you end up with, is just the green plus the red. And the idea with Nesterov momentum, and this ends up working better in practice, is the following. We know at this point, regardless of what the current input was to us, so we haven't computed the gradient step yet, but we know that we've built up some momentum, and we know we're definitely going to take this green direction. Okay, so we're definitely going to take this green. So instead of evaluating the gradient here at our current spot, Nesterov momentum does this one step look ahead, and instead evaluates the gradient at this point, this point, at the top of the arrow. So what you end up with is the following difference. Here, we know we're going to go this way anyway, so why not just like look ahead a bit to that part of the objective and evaluate the gradient at that point. And at that point, of course, your gradient is going to be slightly different because you're in a different position in the loss function. And this one step look ahead gives you a slightly better direction over there. And you get a slightly different update. Now you can theoretically show that this actually enjoys better theoretical guarantees on convergence rates. But not only is it true in theory, but also in practice, Nesterov momentum almost always works better than just standard momentum. Okay, so the difference roughly is the following. Here I've rewritten it in LaTeX notation instead of code. But we still have this velocity vector equals mu times the previous velocity vector and the gradient that you're currently evaluating. And then we do an update here. And so the Nesterov update, the only difference is we're appending here this mu times vt minus 1. When we're evaluating the gradient, we have to evaluate it at a slightly different position, in this look-ahead position. And so that's really a Nesterov momentum. It almost always works better. And now there's a slight technicality here, which I don't think I'm going to go into too much, but it's slightly inconvenient. The fact that normally we think about just doing a forward pass and backward pass. So what we end up with is we have a parameter vector theta and the gradient at that point. But here Nesterov wants us to have a gradient parameter theta and a gradient at a different point. So it doesn't quite fit in with like a simple API that you normally have in your code. And so it turns out that there's a way, and I don't want to really probably spend too much time on this, but there's a way to basically do a variable transform where you denote this to be phi, you do some rearrangement, and then you get something that looks much more like a vanilla update that you can just swap in for momentum, or you can swap it in for SGD, because you end up with only needing gradient at phi, and you do updates on phi. And this phi is really the looked ahead version of the parameters instead of just the raw parameter vector. So that's just a technicality. You can go into notes to check this out. Okay, so here, Nesterov accelerated gradient is in magenta. And you can see the original momentum here overshot by quite a lot. But because the Nesterov accelerated momentum has this one-step look ahead, you'll see that it curls around much more quickly. And that's because all these tiny contributions of a slightly better gradient at where you're about to be end up adding up, and you almost always converge faster. Okay, so that's Nesterov accelerated momentum. So until recently, SGD momentum was the standard default way of training convolutional networks, and many people still train using just momentum update. So this is a common thing to see in practice, and even better if you can use Nesterov accelerated momentum. So NAG here stands for accelerated gradient. Okay, question?
So in practice, how close together are the minima typically? As in, what's that serious risk of like overshooting against practice?
You're asking about the optimization landscape, and you're thinking about minima and whether or not you can maybe overshoot to like a wrong minimum or something like that. So I think it's slightly incorrect to, so when you think about loss functions for neural networks, usually you think about these crazy ravines and lots of local minima everywhere. That's actually not a correct way to look at it. That's a correct approximation to have conceptual in your mind when you have very small neural networks. And people used to think that local minima are an issue in optimizing neural networks. But actually it turns out with a lot of recent, even theoretical work, that as you scale up your models, these local minima just become less and less of an issue. So the picture to have in mind is there are lots of local minima, but they're all about the same, actually, loss. That's a better way to look at it. So these functions, neural networks, actually in practice end up looking much more like a bowl instead of a crazy ravine landscape. And you can show that as you scale up the neural network, the difference between like the worst and your best local minimum, it actually kind of like shrinks down over time with some recent results. So basically, there's no bad local minima. This only happens in very small networks. So, and in fact, in practice, what you find is if you initialize with different random initialization, you almost always end up getting the same answer, like the same loss in the end. So you don't end up, there's no like bad local minima you sometimes converge to, especially when you have bigger networks. Thanks for the question. OK, was there a question over there?
Nesterov has this oscillating feature. How to overcome this?
Nesterov has an oscillating feature? Which part is oscillating? OK, I think you're jumping ahead maybe by several slides. We're going to go into second-order methods in a bit. OK, so let me jump into another update that is very common to see in practice. It's called Adagrad, and it was originally developed in the convex optimization literature, and then it was kind of ported over to neural networks, and people sometimes use it. So the Adagrad update looks as follows. We have this update as we normally see. So this is just basic stochastic gradient descent here, learning rate times your gradient. But now we're scaling this gradient by this additional variable that we keep accumulating. Okay? Note here that this cache, which we're building up and is the sum of gradients squared, this cache contains positive numbers only. And note that the cache variable here is a giant vector of the same size as your parameter vector. And so this cache ends up building up in every single dimension. We're keeping track of the sum of squares of the gradients, or as we like to sometimes call it, the second moment, although it's the uncentered second moment. And so we keep building up this cache, and then we divide element-wise this step function by the square root of cache. And so what ends up happening here, let's see, so that's the reason that people call it a per parameter adaptive learning rate method, because every single little dimension of your parameter space now has its own kind of like learning rate that is scaled dynamically based on what kinds of gradients you're seeing in terms of their scale. So with this interpretation, what happens with Adagrad in this particular case if we do this? What happens in the horizontal and vertical direction with this kind of dynamics?
Scaling up the horizontal movement, the gradients, and you're scaling down the vertical.
OK, that's correct. So what you'll see is we have a large gradient vertically, and that large gradient will be added up to cache, and then we end up dividing by larger and larger numbers, so we'll get smaller and smaller updates in the vertical step. So since we're seeing lots of large gradients vertically, this will decay the learning rate, and will make smaller and smaller steps in the vertical direction. But in the horizontal direction, it's a very shallow direction, so we end up with smaller numbers in the denominator, and you'll see that relative to the y dimension, we're going to end up making faster progress. So we have this equalizing effect of accounting for this steepness. And in shallow directions, you can actually have much larger learning rate than instead of the vertical directions. So that's Adagrad. One problem with Adagrad is think about what happens to the step size as we're updating this position. If we want to train an entire deep neural network, this takes for a long time, and we're training this over a long time, what's going to happen in Adagrad? OK, of course. So your cache ends up building up all the time. You add all these positive numbers, goes into your denominator. Your learning rate just decays towards 0, and you end up stopping learning completely. And so that's OK in convex problems, perhaps, when you just have a bowl and you just kind of decay down to the optimum and you're done. But in a neural network, this stuff is kind of like shuffling around, and it's trying to fit your data, and that's like a better way to think of it. And so this thing needs continuous kind of energy to fit your data. And so you don't want it to just decay to a halt. So there's a very simple change to an Adagrad that was proposed by Jeff Hinton recently. And the idea here is that instead of keeping a completely just the sum of squares in every single dimension, we make that counter a leaky counter. So instead, we end up with this decay rate hyperparameter, which we set to something like 0.99 usually. And then what you're doing is you're accumulating the sum of squares, but the sum of squares is leaking slowly with this decay rate. Okay? So we still maintain this nice equalizing effect of equalizing the step sizes in steep or shallow directions, but we're not going to just converge completely to 0 updates. So that's called RMS prop. One nice historical fun fact about RMS prop, by the way, is the way it was introduced was, you'd think that it would be a paper that proposed this method, but in fact it was a slide in Jeff Hinton's Coursera class just a few years ago. And so Jeff Hinton just was giving this Coursera class, and he flashed this slide of like, oh, this is unpublished, but this usually works well in practice. And do this, and it's basically RMS prop. And so I implemented it, then I saw like better results on my optimization right away, and I thought that was really funny. And so in fact, in papers, not only my papers, but many other papers, people have cited this slide from Coursera. You just slide lecture 6, this slide, just there's RMS prop. Since then, this is actually now an actual paper, and there's more results on exactly what it's doing, and so on. But for a while, this was really funny. And so in this optimization perspective, we can see Adagrad here is blue, and RMS prop is this in black. And we can see that both of them converge quite quickly down here this way. In this particular case, Adagrad ends up converging slightly faster than RMS prop. But that's not always the case. Usually what you see in practice when you train deep neural networks is Adagrad stops too early, and RMS prop will end up usually winning out in these methods. Any questions about Adagrad, RMS prop? Go ahead.
Since you scale down the learning rate in the steeper direction, if the, like in that image that you had,
oh, sorry.
red dot.
Where's this image?
Yeah, if it was moved over where it's like directly under the smiley face, like don't you want it to just go quickly down the steepest direction?
So you're saying that in some cases you might want to actually make faster progress in steeper direction. The issue is, in this particular case, maybe that's true, but in general, if there are very steep directions, you probably don't want to. This method is saying don't make very fast updates in that direction, slow yourself down. So maybe in this particular case, you'd like to go faster, but you're kind of reading into this particular example, and that's not true kind of in general in these optimization landscapes that neural networks are made up of. So this ends up being a good strategy kind of to apply in those cases. Go ahead.
So in this Adagrad / RMS prop, why do we still need the learning rate? Because you have a scaling parameter on the weights anyways, right?
Yeah, but so in the beginning, oh, by the way, I skipped over this explanation of 1e-7, but you guys can hopefully see that 1e-7 is there just to prevent a division by 0. It's a smoothing factor. It's a hyperparameter. Usually we set it to 1e-5 or 6 or 7 or something like that. In the beginning, your cache is 0. So then you increment your, like you still need the learning rate to, what you get is this adaptive behavior, but the scale of it is still in your control. The absolute scale of it is still in your control. You still need a learning rate for this. Go ahead.
Why do we track the cache?
Like what it's doing, oh, sorry, just to interrupt. It's kind of doing, you can look at more like a relative thing with respect to different parameters. How are you equalizing the steps? But the absolute global step is still up to you. Go ahead.
Why do we track the cache from the very beginning instead of, for example, just the last 100?
Why do we cache from the very beginning instead of the last 100? Thank you. So RMS prop is effectively doing what you're describing, right? Because it ends up forgetting sort of gradients from very long time ago. And it only really, its expression at time t is only a function of the last few gradients, but in an exponentially decaying weighted sum. Okay, cool. So that's RMS prop. We're going to go into last update. Go ahead.
People tried using like a window, like the last, let's say, 10 x squared values that are summed together.
So you want to have a finite window over which you're summing up these gradients?
Yeah.
So would it be similar to RMS prop, except... so RMS prop is already adding up your gradients from the past in an exponentially weighted way. And so you want to have a finite window on this? Or I don't think people have really tried. You can.
It takes too much memory.
That's what I was thinking.
Yeah, it takes too much memory.
Although LBFGS kind of has that flavor, but people don't really use that in practice very much.
Okay.
Yeah, so once you're optimizing neural networks, you'll see that X, for example, has 140 million parameters. So that's taking up quite a lot of memory. And so you don't want to keep track of 10 previous gradients and so on. OK, so the last update we're going to go into. Oh, sure.
Could you combine Adagrad with momentum?
could you combine Adagrad with momentum? Thank you for the question. Yes, you could, and that's this slide. So, so roughly what's happening is Adam is this last update that was only actually proposed very recently, and it kind of has elements of both. As you'll notice, momentum is kind of keeping track of the first order moment of your gradient. It's summing up the raw gradients, and it's keeping this exponential sum. And Adagrad and so on are keeping track of the second moment of the gradient and its exponential sum. And what you end up with is an Adam update is you end up with the step that's basically it's kind of like, let's see, it's kind of like RMS prop with momentum a bit. So you end up with this thing that looks like it's basically keep track of this velocity in a decaying way, and that's your step. But then you're also scaling it down by this exponentially adding up a leaky counter of your squared gradients. And so you end up with both in the same formula. And that's Adam update, combining those two. Okay? So you're doing both momentum, and you're also doing this adaptive scaling. And let's see. So here's the RMS prop, actually. I should have flashed this earlier. So when you compare this, basically RMS prop in red is the same thing as here, except we've replaced dx, which there was just a gradient currently right now. We're replacing this gradient dx with m, which is this running counter of our dx. So if you imagine, for example, one way to look at it also is you're in a stochastic setting. You're sampling mini batches. There's going to be lots of randomness in a forward pass. And you get all these noisy gradients. So instead of using any gradient at every single time step, we're actually going to be using this decaying sum of previous gradients. And it kind of stabilizes your gradient direction a bit. And that's the function of the momentum here. And the scaling here is to make sure that the step sizes work out relative to each other in steep and shallow directions. Go ahead.
So how do you decide on beta 1 and beta 2?
Thank you. Beta 1 and beta 2 are hyperparameters. Beta 1 usually 0.9, beta 2 usually 0.995. Somewhere there. So it's a hyperparameter. You have to cross-validate over it. In my own work, I found that this is a relatively robust settings across. I don't actually usually end up cross-validating these. I just set them to fixed values usually. But you can play with those a bit, and sometimes it can help you a tiny bit. Okay? Cool. Go ahead.
Can you combine Nesterov moment with Adagrad?
Thank you. So the question is, can you combine Nesterov momentum with Adagrad? So here, this is like a vanilla momentum. We saw that Nesterov momentum works better. Can you do that? Yes, you can. I actually just read a paper about this yesterday. And actually, it wasn't a paper. It was a project report from 229. Someone actually did that. I'm not sure if there's a paper about it. But yeah, you can play with that, certainly. That's not being done here. OK. One more thing that so I have to make Adam slightly more complex. Here, as you see, it's incomplete. So let me just put in the full complete version. In Adam, there's one more thing where you might be confused when you see it. There's this thing called bias correction that they insert there. And this bias correction, the reason I'm expanding out the loop is that the bias correction depends on your absolute time step t. So t is used here. And the reason for that is what this is doing is kind of like a minor point, and I don't want anyone to be confused about this too much. But basically, it's compensating for the fact that m and v are initialized at 0. So your statistics are kind of incorrect in the beginning. And so what it's doing is really it's scaling up your m and v at the first few iterations, so you don't end up with a very kind of biased estimate of the first and the second moment. So don't worry about that too much. This is only changing your update at the very first few time steps as the Adam is warming up. And so it's done in the proper way in terms of the statistics of m and v. Okay? I don't want to go too much into that. Okay, so we talked about several different updates, and we saw that all of these updates have this learning rate parameter still there. And so I just wanted to briefly talk about the fact that all of these still require a learning rate, and we saw what happens with different choices of learning rates for all of these methods. The question I'd like to pose is, which one of these learning rates is best to use? Maybe not a well-formed question. I'm trying to trick you. It's a trick question. So when you're running neural networks, this is a slide about learning rate decay. The trick answer is that none of those are good learning rates to use. What you should do is you should use the high learning rate first, because it optimizes faster than the good learning rate. You see, you make very fast progress, but at some point you're going to be too stochastic and you can't converge into your minima very nicely because you have too much energy in your system and you can't settle down into like nice parts of your loss function. And so what you do then is you decay your learning rate, and then you can kind of ride this wagon of decreasing learning rates and do best in all of them. So there are many different ways that people decay the learning rates over time, and you should also decay them in your assignment. There's step decay, which is kind of like the simplest one perhaps, where after one epoch of training data, epoch is referring to you've seen every single training example one time. So after, say, one epoch, you decay the learning rate by a factor of 0.9 or something like that. You can also use exponential decay or 1/t decay. There's several of them. I go into notes slightly expanding on some of the theoretical properties that have been proven about these different decays. Unfortunately, not many of them apply because I think they're mostly from convex optimization literature, and we're dealing with very different objectives. But usually in practice, I just use exponential decay or something like that. Was there a question? Go ahead.
Yeah, I was going to ask the same question about the convergence algorithms. Could you skip from one to the next, like use momentum to accelerate your losses at a certain point and then switch to something that's going to converge faster?
I see. So you're asking about not committing to any one of these, but you want to also like shift between them during training. Yeah, I don't think that's standard at all. That's an interesting point. I'm not sure when you'd want to use. Yeah, it's not clear to me. You could try that in your assignment. That's a fun thing to try. In practice, I'd like to make the point that you almost always, I find, at least in practice right now, Atom is usually the nice default choice to go with. So I use Atom for everything now, and it seems to work quite well. Better than Momentum or RMS prop or Adagrad or anything like that. Okay, cool. So these are all first order methods, as we call them, because they only use your gradient information at your loss function. So we're evaluating the gradient, and we basically know the slope in every single direction, and that's the only thing that we use. There's an entire set of second order methods for optimization that you should be aware of. The second order optimization methods, I don't want to go into too much detail, but they end up forming a larger approximation to your loss function. So they don't only approximate it with this basically hyperplane of like which way are we sloping, but you also approximate it by this Hessian, which is telling you how your surface is curving. So you don't only need the gradient, you also need the Hessian, and you need to compute that as well. And you may have seen a Newton method, say for example in 229. So in Newton method, it's basically giving you an update that once you've formed your bowl-like Hessian approximation to your objective, you can use this update to jump directly to the minimum of that approximation, and then you iterate the scheme. So what's nice about second order methods? Why do people like these or use them? Especially the Newton method is presented here. What's nice about this update? Faster convergence.
Less hyperparameters.
Thank you. Less hyperparameters. You'll notice no learning rate, no hyperparameter in this update. Okay? And that's because if you see your gradient in this loss function, but you also know the curvature in that place. And so if you approximate it with this bowl, you know exactly where to go, to the minimum of your approximation. So there's no need for a learning rate. You can jump directly to that minimum of that approximating bowl. So that's a very nice feature. I think those are the two that I had in mind. You have a faster convergence because you're using second order information as well. Why is it kind of impractical to use this step update in training neural networks? Good.
Your Hessian will be gigantic because you have way too many parameters.
Yeah. So the issue, of course, is Hessian. Say you have a 100 million parameter network. Your Hessian is 100 million by 100 million matrix, and then you want to invert it. So good luck with that. So this is not going to happen. So there are several kind of algorithms that I'd just like you to be aware of. We're not going to use them in this class. But just be aware that there's something called BFGS, which basically lets you get away with not inverting the Hessian. It builds up an approximation of the Hessian through successive updates that are all rank 1, and it kind of builds up this Hessian. But you still need to store the Hessian in memory, so still no good for large networks. And then there's something called LBFGS, short for limited memory BFGS, which does not actually store the full Hessian, or it's approximated in inverse, and that's what people use in practice sometimes. Now, LBFGS, you'll see it sometimes mentioned in optimization literature especially. What it works really, really well for is if you have a single small deterministic function like f of x, there's no stochastic noise, like there's no stochasticity in f, and everything fits in your memory, then LBFGS can usually crush these loss functions very easily. But what's tricky is to extend LBFGS to basically very, very large data sets. And the reason is that we're subsampling these mini batches because we can't fit all of the training data into memory. So we subsample mini batches, and then LBFGS kind of works on these mini batches, and its approximations end up being incorrect as you swap different mini batches. And also the stochasticity, you have to be careful with it, and you have to make sure that you fix dropout. You have to make sure that your function, so internally LBFGS calls your function many, many different times as it's doing all these approximations and line search and stuff like that. It's a very heavy function. And so you have to make sure that when you use this, you disable all sources of randomness because it's really not going to like it. So basically, in practice, we don't use LBFGS because it seems to not work really well right now compared to first-order methods. It's basically too heavy. Too much stuff is happening, and it's better to just do this noisier stuff, but do more of it. That's the trade-off. So in summary, use Atom as a good default choice. And if you can afford to, you can afford full batch. So maybe your data set is not very large, and you can afford to have it all in memory and do all the forward and negative passes in memory. Then you can look into LBFGS. But you won't see it in practice used in any large-scale setting right now, although it's research direction right now. All right, so that concludes my discussion of different parameter updates, decay or learning rates. We're not going to look into LBFGS in this class.